fired up at 8.9 kilometers per second. Find the maximum height. So basically, what we're trying to do is we have an initial kinetic energy, right? Initial speed, which is 8,900 meters per second, because you're just multiplying by 1,000. So you have initial kinetic energy, and then I'll just call this MP. And then you have initial gravitational potential energy, right? Because it's on the surface. It was fired on the surface of the Earth. So GMP ME over RE. And then that would all have to be equal to the final kinetic energy and the final potential energy. But remember, when when the potential energy is at its max, there is no kinetic energy at all. Just like in projectile motion, when it's at its max height, the velocity is zero. So there's no kinetic energy in the final state. But there is potential energy. And we're trying to find the maximum height here. So it wouldn't be like the distance between the two centers. No, it's just the difference between the ground and how high it goes. Like if I were to draw it, this right here is h, but this right here is r, and we usually use h plus r when we're solving these problems, which we are gonna do, but we're gonna try to solve for h. So me, and then re plus h. So what I'm going to do is I'm going to divide both sides by 1, because this is like the least ugly way to solve this without like adding fractions and such and simplifying everything. So we get 1 over 1/2 MP V squared minus G MP ME over RE equals RE plus H over negative G MP ME. So I'm going to multiply both sides by negative G MP ME, and then I'm going to get negative G MP ME over 1/2 MP V squared minus G MP ME over RE. So all these masses cancel out, and then we're just left with RE plus H. So what I'm going to do is subtract the radius of the Earth from both sides, so we get negative G ME over 1/2 V squared minus G ME over RE minus RE equals the height. And then that would be roughly equal to around 109,634,664. So about 10,963,464 meters. And the most evidence, the most advanced telescopes have only seen evidence of planets orbiting nearby stars or extrasolar planets. Suppose a planet has a 1270-day period as it orbits a star with the same distance of Jupiter from the Sun. Find the mass and solar masses. And one solar mass is the mass of the Sun. So another thing to know is that distance between Jupiter from the Sun is 7.78 times 10 to the 11th meters. And it will also be nice to calculate this in seconds, so all the SI units match up. So 1270. So the period would be 1270 times 24 times 3600 seconds. So basically, because it's in orbit, it's going to have a centripetal force. So we can apply centripetal acceleration to this. So this is the mass of the planet times v squared over r equals g times mass of the planet times mass of the star over r squared. And then the mass of the planet cancels out. So we get v squared over r equals g times mass of the sun over r squared. The thing is, we do not know speed, but we do know the period. And we know that velocity is related to period by the circumference of a circle over time. So we know these two are related by this equation. And 2 pi is a constant, and we know the radius, and we know the period because we just calculated that. So basically what we can do is we can sub in this for v, and then we could just solve for the unknown mass of the sun. So when we plug that in, so we get 4 pi squared r squared over t over r. So this would just be simplified to 4 pi squared times r over t. And then that would equal g times mass of the star over r squared. So, and then this should be t squared because you're squaring the velocity. So what you have to do is you have to multiply both sides by r squared. So you get 4 pi r cubed over t squared, and that would equal g times mass of the star. And then you just divide by g, and then you get 4 pi r cubed over t squared over g ms. G, just g. And then equals ms. But that's just the mass in kilograms. So what we have to do is we have to divide by the mass of the sun. Or we have to find the solar mass by mass of the sun. So what we just have to do is just divide by the mass of the sun, which is around, and the mass of the sun is around 2 times 10 to the 30th kilograms. So when you calculate everything correctly, it should be around 11.6 solar masses. I'll just say SM.